So, good morning, everyone. So today's topic is on local optimizations. So in the last class, we have seen that all modern compilers, they have a front end and an optimizing middle end and a back end. So now our focus is on the middle end of the compiler, the optimizing middle end of the compiler. So when we consider this, the optimizing middle end of the compiler, the optimization passes that are present in the middle end of the compiler, they can be classified into different types depending upon the granularity or the scope at which they work. There are some kind of optimizations which we will see in today's class which work at the basic block level. And these are called as local optimization techniques. So techniques which work, optimization techniques which work within a basic block level, they are called as local optimization techniques. So that's what we will see in today's lecture. And there are certain optimization techniques which go beyond loops and within a function or within a procedure, but within a control flow graph, within a control flow graph associated with a procedure or a function, these techniques will work, but the region that they consider is more than one basic block. So for example, in the next class, we will look at what are called as extended basic blocks. Something happened, just give me a minute. Extended basic blocks. And then we also look at beyond extended basic blocks, we use what is called as a dominator region and learn how to apply specific optimization on a dominator region in the next class. And then there are techniques which work at a whole function level. Recall that we have seen how to construct a control flow graph, and a control flow graph is associated with a specific function in the program. So for every function that is present in your program, you will have an associated control flow graph. And there are what are called as intra-procedural techniques or global optimization techniques which work at the procedure level or at the control flow graph level. So here I want you to understand, usually we keep saying global optimization techniques, but global means at the level of a function, not at the level of a file. And there are optimization techniques which work across procedures or across functions. And these are called as interprocedural techniques. In this course, we will not see any interprocedural optimization techniques. And there are optimization techniques which work across files. Remember, you may recall or know that if you go beyond small programs, your software is developed, the source code for your project will be spread across multiple files. So these interprocedural techniques, they work at the level of a file, but then there are what are called as link time optimizations, which kind of work across files. So what happens in link time optimizations, let's say your source code is present in file1.c to, let's say, file9.c. There are 9 files across which your source code is spread out. So your each of these files, from each of these files, the compiler generates object the compiler generates object files, and these are optimized object files. And in the process of generating file1.o from file1.c, the compiler would have applied some local techniques, some regional techniques, some global techniques or intra-procedural techniques, and some inter-procedural techniques. But all these optimization techniques, they work within the file. So now, but whereas the link time optimizations, they consider all these object files together, and so before the final executable is generated, so before the final executable is generated, so these cross inter-object file optimizations will be performed. These are called as link time optimizations. And after all these link time optimizations are performed in a.out file or whatever the executable file it will be generated. Again, we will not study any link time optimizations in this course, but we will definitely study local techniques in today's lecture, regional techniques in the next lecture, and later on we will spend at least 1 or 2 classes on intra-procedural techniques. So this is the plan for the next 3-4 lectures. So when a compiler is trying to perform optimization at a particular scope or level, it creates some kind of data structures. For example, while working at the basic optimization techniques which work at the basic block level, depending upon the kind of optimization that is being done, certain data structures will be created. For example, in order to do instruction scheduling, a data structure called as dependency graph will be constructed. And in today's lecture, where we do common sub-expression elimination at within a basic block, you will see what kind of data structures will be created by that optimization pass. And when optimizations are being done at a regional level, so like for example, if you are working on, we will see an optimization pass called as dominator based value numbering technique. So when we are applying this dominator based value numbering technique, so we have to construct what is called as a dominator tree. So depending upon what kind of regional technique it is, the corresponding data structure needs to be created. And of course, when we are working at a procedure level, then we have to construct the control flow graph associated with that function. And along with the control flow graph, several other data structures such as def use chains, use def chains, or an SSA representation of the program, these kind of data structures will be created. And when the compiler is working at an interprocedural level, then call graph, that is which function is calling which functions. So a call graph will be constructed, and along with the control flow graph of each of the functions, this call graph will also be used to guide the interprocedural optimization techniques. We have already seen in a couple of classes back, when we talk about these optimization passes, there is a distinction between analysis passes and transformation passes. The analysis passes kind of derive information about the program statically at compile time. And then this analysis information is used by the transformation passes to rewrite the code or to transform the code so that a better quality code will be obtained. So there is a distinction between these analysis passes and transformation passes. One interesting thing though is when we are working within a basic block, or when we look at these local optimization techniques, usually the analysis pass and transformation pass, they are interleaved with each other. For example, the common sub-expression elimination technique that we are going to see today, you can see that the analysis and transformation passes, they are interleaved together. But when we consider optimizations at a higher, which work at a larger scope, like at a procedure level or at a function level, then the analysis pass will first go through and it derive all the necessary information, followed by that a transformation pass. So to summarize, in local optimization techniques, it is quite possible that the analysis and transformation passes could be interleaved with each other. But optimization techniques which work at a higher scope, like at a extended basic block level, or at a dominator region based level, or at a function based level, or at a interprocedural level, it is very normal to have an analysis pass which collects all the information, and then the transformation pass starts doing its job. So now let's look at, in the last class, we have seen global common sub-expression elimination technique. Through an example, we didn't exactly see the algorithm, but we have seen what this optimization is through an example. And in a later class, we will come up with an algorithm to do that. But we know what that optimization is supposed to do. Consider the basic block that is there on the top left side, that is the original block. So there are four expressions, four statements here, four tuples here. And you can see so you can see by visually looking at the code, so you have B plus C here and B plus C here. So we may think that the value computed by this first evaluation of B plus C could possibly be used here. But then on a deeper analysis, we can note that the second tuple modifies the operand B. Because of that, the value of the expression at this point is different from the value of the expression at this point. So it is not actually a redundant computation. But on the contrary, if you see this A minus D, so A minus D is evaluated here, and then A minus D is evaluated here. Between the first computation of A minus D and second computation of A minus D, the operands A and D are not modified in between. So because of that, the value that is obtained at the second computation is same as the value that is obtained at the first computation. So due to that, this value can be propagated, this value that is computed here, it can be propagated here. And that's what is being done here. So the value that is computed here is stored in variable B, and it is propagated to the fourth tuple here. So this is how global common sub-expression elimination works within a basic block. Now let's consider the code that we have here in this basic block. So visually speaking, we can notice that the computation here and the computation here, they result in the same value, although the two expressions B times C and D times C, they look differently when we do a textual comparison of the operands, because here we have the operand B, and here we have the operand D. So when we compare the two expressions B times C and D times C, they are different textually speaking. But with respect to value, they are the same, because the value that is being computed here at, at this point, and the value that is being computed here, they are exactly the same because of this assignment statement. D is equal to B. So we have to, in order to factor in this, if you just try to do redundant computation elimination purely based on identifying common sub expressions textually, we will lose out on, we may lose out on optimization opportunities. In order to solve this problem, a technique called as value numbering technique is being proposed. So let's see what this value numbering technique is with the help of an example. So let's consider a sequence of statements here. Let's consider a sequence of statements. A is equal to B plus C. B is equal to A minus D. C is equal to B plus C. D is equal to A minus D. So we have this sequence of tuples, and this is how the value numbering technique works. In the value numbering technique, we maintain three data structures. One data structure is called as a variable to value number. Vn stands for value number, Vn map. So this is one data structure. Another data structure is value number to variable map. This is another data structure. And there is another data structure which is a hash table. So these are the three data structures we will maintain. So Vn stands for value number. This is what is called as a value numbering technique. So let me use, yeah. So what happens is, so the value numbering technique, it starts with the first tuple and it looks at the variable B and it gives a, and variable B contains some value. It can be any value, and we give a name or a number to that value that is present in variable B. Let's call it as 0. So if you see, variable B contains value number 0, and then we have a value number to variable map. We say value number 0 is present in variable. And then we go to variable C. So variable C contains some value. We give it some number. We say variable C contains a value whose name is 1, and the value number 1 is present in variable C. So this is what we do. So now value 0, when I say value 0, so it's not 0, but the value whose name is 0 and is added with value 1, and a new value will be created. So what we do is we go and check in the hash table if this computation is already being done. And right now, if you see, the hash table is completely empty. So yeah, it's not, we don't get anything out from the hash table. And so we say that when you add value 0 to value 1, you get value 3. And this we will make an entry here. So 0, 1, it is present in 3. And then here we have 3 is present in 3. Now we go to the second tuple. The algorithm goes to the second tuple. So it looks at the variable A. It goes and looks at the variable to value number map. We know that the variable A is holding value number 3. So this is 3. And again, the second operand here is D. You go and look at a variable to value number map. D doesn't have any value number, prior value number. So whatever the value that is present in D, let's call it as, I think let me use, this is 2, 2, 2, 2, 3. So variable D now contains 3, 3 contains D. And when value number 3 is subtracted from value number 2, so we want to go and check in the hash table if this particular computation is already being done. But if you go and check in the hash table, it's not available. So we make an entry into the hash table in this particular. And it creates a new value 4 and B gets 4. So now when B gets 4, so what happens is we have to change this variable to value number map and value number to variable map. So now B contains 4 and value number 4 is present in B. And when this tuple, this tuple is already processed, this is processed. Now we are processing this tuple. And when we are processing the tuple C is equal to B plus C, again, you go and check this data structure. We know that B contains value number 4 and C contains value number 1. And we go and check the hash table. It's not there. So we make an entry into the hash table and we generate a new value 5. So now C contains the new value 5. So what should we do? So we should. So this is how, as the data structure, as we keep progressing, as the algorithm keeps progressing, this is how the data structures are being updated. And then, so here we have, let's now come to D is equal to A minus D. So what is A? The value number associated with A is 2. The value number associated with D is 3. You go and check in the hash table. So we know that when we subtract value number 3 from value number 2, you get value number 4. And so now you go and check this value number to variable map. You know that value number 4 is present in variable 4. So this is what happens. So now actually what we can do is at this point, we can eliminate this, we can replace this tuple D4 with B. This is not D4, so this D is equal to B because we know that the value number 4 is present in variable B. And now what we do is we do one more thing here. So as a part of this thing, so now D contains value number 4 and value number 4 is present in variables B and so as you can see, we keep processing the tuples one at a time, and we can interleave transformations with the analysis logic. So, for example, on line 4 or the tuple 4, we are able to immediately replace or eliminate the redundant computation A minus D. And we can kind of make this technique more extensive by saying whether it is B plus C or a value number 0 plus 1 or 1 plus 0, it is the same if 0 and 1, if they are holding integer values. If 0 and 1 are holding integer values, then integer addition is commutative. So whether you are adding 0 and 1 or 1 and 0, it's the same. So we can kind of extend this value numbering technique in order to include more cases and thereby increase the optimization opportunities. So let's come back and see. This is all about a value numbering technique. This is the crux of the value numbering technique. Let's come and see some more examples. So here is yet another example. So in this example, this is the original code. A is equal to x plus y, b is equal to x plus y. And when you do the value numbering technique, you can immediately see. So when we are accessing uh, the initial value that is present in x, we can give a value number 1. And the initial value present in y, we can give a value number 2. So value number 1 plus value number 2, it generates a new value number 3. So the value numbers associated with x and y, they are not changing. So they just remain the same, 1, 2. But we know that, while processing the tuple, 1, 2 is present in value number 3. So we will say B holds the value number 3. So in this picture, although we didn't replace what we have on the RHS, we can actually remove it and change it to A. So it works perfectly fine. And then when this tuple is being processed, so we have A is equal to 17. A now contains a new value number 4. We call it as 4. And x and y still contain 1 and 2. So there is one, so maybe it's a good idea to go through this bit carefully, so that way there is a point that we would like to illustrate that comes out much more clearly. Let me go a bit slow on this. So let's start with here. So initially we, as you know, so we have a variable to value number map. So x is present, contains 1, value number 1, and value number 1 contains x. This is 2, 2 contains x, and then 1, 2 contains 3. And we come to the second tuple. When we are working with the second tuple, we know that, so from here, x contains value number 1, y contains value number 2. 1 plus 2 is nothing but value number 3. So B contains value number 3. And we can actually replace this x plus y with A, because A contains the value number 3. And so what happens here is you have B now contains 3, and 3 value number 3 is present in variables A and B. This is the story so far. But when we are working, when the statement A is equal to 17 is being processed, then A gets a new value number. A gets a new value number 4. A gets a new value number 4. This is 3. And value number 4 is present in A. So now value number 3 is present in only variable B. And when a statement C is equal to x plus y is processed, so x has still value number 1, y has value number 2, and 1 plus 2 is 3, and value number 3 is present in variable B. So we can replace this x plus y with B. So as you can see, finally, this is the code that we can get at the end. So actually, we can replace this also with A without any problem. So I hope you're all with me here. So if there are any questions, you can ask me now. Are you all with me so far? If you're all doing all right, can you respond back in the chat box so that I see? Okay, thank you. So let's move on. Next example is an interesting example, and that leads us to a the most important concept in compilers. So please pay attention uh, here. So if you see this code, a is equal to x plus y, and the sequence of three tuples, you can see that that x plus y here, the computation x plus y here, it is a redundant computation. But the problem is this x plus y, the value that is computed here, we cannot propagate it here because it is stored in a variable a, and variable a is modified. The important idea here is if you see variable a, it has two definition points. So this is definition point 1 and this is definition point 2. So there are two definition points, and so what is happening here is the value that is being used here, that the value that is being computed here in this tuple, it is a redundant computation because that value is already available as a result of computing this tuple. But unfortunately, we cannot say C is equal to A. It doesn't work because the variable A is redefined in the intervening path. So how do we solve this problem? So one way of solving this problem is we can introduce a temporary variable like here t is equal to a, and then so the value, then this permits then we can use the variable t here in order to eliminate the redundant computation. So this is one possible approach. We don't want the value that is being computed to be destroyed. So since we don't want to get it destroyed, we copy it to a compiler generated temporary variable, and so that that value can be reused later. So this is one approach, but this is not quite an elegant approach. So instead, we use a representation called a static single assignment form representation. So we take the original code and transform it into what is called as an SSA form. In SSA form, every time a variable gets defined uh, in the program text, a new version of the variable will be created. So here we are defining variable for the first time. So we are creating the 0th version of the variable, and we are calling it as A0. Similarly, here we are defining variable b for the first time. So we are creating a 0th version of the variable and we are calling it as b0. And here we are defining a for the second time. So we generate a new version or avatar of the variable and we are calling it as a1. Similarly, here we are creating a version of the variable c0. So if you look at a program that is converted into static single assignment form, every variable will have only exactly one definition point. So A0, B0, A1, C0. So you never see a variable on the left occurring on the left hand side two times. And why is it a static single assignment form? For example, this basic block could as well be present in a loop. Okay, so this could be, this is an entry basic block. This is the exit basic block. So if you look at this loop, dynamically when the program is executing, this same statement can be executed multiple times. But with respect to the program text, there is only one place at which, there is only one definition point. So from the variable A here, we are generating new versions of the variables. And if you see the new SSA form of the code, the most important thing is every variable is defined exactly once. And when we say every variable, A0 is a different variable from the variable A1. Agreed that they came out from the same variable A from the original program text, but in the transformed namespace, in the new SSA namespace. So what we are doing is, there is an original namespace. There is an original namespace for the program. From the original namespace, we are creating what is called as an SSA namespace. So in the original namespace, you have the variables A, B, X, Y. And in the transformed namespace, we have the variables A0, A1, B0, C0, X, Y. So here X should also be, C also should be present. So in the transformed namespace, in the SSA namespace, every variable occurs, be it A0 or A1 or B0 or C0, it occurs on the LHS exactly once. But when the program is executed, it is possible that the same variable is assigned value multiple times dynamically. So this is what SSA form is. And if a program is in SSA form, many optimizations becomes easy. All right. So let's look at this example. In this example, so this is the original namespace and this is SSA form. And if you do a value numbering technique here in this thing, so here 1, 1. So variable X is present in value number 1. So variable Y is present in value number, variable Y contains value number 2. So value number 1 is present in X. Value number 2 is present in Y. And then 1 plus 2, it's a new value number. It is 3. And so this is 3. So here we say the variable A0 contains 3 and value number 3 is present in variable A0. And then again here we have 1, 2 and 1 plus 2 is 3. So what we have is B0 also contains 3 and 3 is present in A0 and B0. And when we go here, so A1 contains, the variable A1 contains value number 4 and value number 4 is present in variable A1. And then here, so this is again 1, 2. So 1 plus 2, it gives the value number 3. And if you go and check this table, the value number 3 is present in two variables A0 and B0. So we can actually replace this X plus Y with either A0 or B0 without any problem, A0 or B0. And what we do is we say C0 contains value number 3 and value number 3 is present not only in A0, B0, it is also present in C0. So like this we can, the value numbering algorithm unfolds. So now we can clearly see without any problem, the values that are computed before, they are naturally propagated to this place and this redundant computation can be eliminated and we don't need to do anything extra in the algorithm per se. The algorithm remains the same, but before we apply the algorithm, we want to transform the code from the original namespace to SSA namespace or SSA form. So all this happens within a basic block, but let's say if you are moving out of the basic block, because we know, so this is basic block is part of the bigger control flow graph. So there are multiple, there can be multiple inflows, predecessors to a basic block, and there can be multiple successors to a basic block. And so when we move out of this basic block, the namespace that you have created for, or the different versions of the variables that we have created within this basic block, they may not be, the other basic blocks may not be aware of them. So how do we solve this problem? One way of solving this, reconciling the namespace between two different basic blocks is, after you are done with processing your basic block, at the end of the basic block, you can copy the latest version of the variable into the original copy of the variable. Like for example, here we can say A is equal to A1, B is equal to B0, C is equal to C0. And then after we did this copy operations, when the control flow goes to other basic blocks, then the latest values of the variables ABC are available, and the execution happens without any violation of the semantics. You may start wondering, hey, this is too many copy operations that we are doing. Whatever the benefits that we are getting through redundancy elimination, etc., we are replacing them with expensive copy operations. So is it all worth it? So if you're thinking along, if you're thinking in the direction, then that means you are thinking right. So what we are doing here is suboptimal. So we want to, instead of transforming the code from the original code to SSA form at the basic block level, we want to work at the whole control flow graph level. Let's see how we can do that. So this we have already seen. Yeah, so this is all good. So this, just before we go further, when we are translating original code to SSA code, to SSA form, within a basic block, it's very easy. So here, this is version 0 of the variable. This is version 0. And so version 0 is whatever the values, variables x and y, not the values. So when the program starts, so there is a default version to the variables. Let's call them as x0 and y0. So here it becomes a1, and then what we do is, so this a1, so we have to, this use of a, we have to replace it with a1, because this is the definition that gets propagated here. And similarly, so now a is equal to a plus 3, right? So a1 plus 3. So now there's a new definition. So you put a2 is equal to a1 plus 3. And here you use x0, y0, and then you create b. So if you are thinking, if you think that this is a program with a single basic block, and this is the entry basic block, and this is the exit basic block. The way to think about is, this control flow graph corresponds to some function, and this function is called. And when this function is called, so what are the possibilities? The variables x and y could be global variables, or they could be parameters. So when we are using them for the first time, these variables x and y, for example, here, we just say use version numbers 0, x0, y0, for example, here. And when we are, there could be a version a0 of the variable that could be entering this function call. But here we have a definition, so that a0 gets overridden with, we create a new version of the variable a1, and any subsequent use of variable a within this basic block, we replace it with a1. And then you have another definition here, a is equal to a. So you create another version of the variable a, and we call it as. So it is intuitive enough within a basic block, so nothing really hard. Now let's take a look at how this works at a slightly bigger level. So we have this is the control flow graph. So x is equal to 5. So we are defining x for the first time. So it gets the version x1, and that's what you are seeing here. And this definition gets propagated to this use. I want to understand this statement, this propagation of a definition to a use. So here, this definition x1 is getting propagated to this use. So we replace this use of variable x with the corresponding definition. So we replace this x with x1. We replace this x with x1, and that's what we are doing here. And now we have a new definition, and this new definition on this tuple, it creates a new version of the variable, and that is x2. And what is the definition that is getting propagated to this use? That is the definition x2. You can see that there are two definitions, x1 and x2. The second definition, x2, within this basic block is jamming the first definition, x1, to reach this particular use. So there is only one particular definition reaching this use, and that particular definition is x2. So we replace this x with the x2, and that's what we are doing here. So now let's go to this basic block. In this basic block, the definition that is reaching this use, that there is a use of x, the definition that is reaching this use is the definition x2. The definition x2 is reaching this use. Similarly here, this, so we'll come to this basic block later, and we are defining y for the first time. So we are generating a new version of the variable y1. And the definition that is being propagated to this use of y is the definition y1. So we replace this y with y1, and we are defining w for the first time here. So we here say w1 y. And here you have x2. So you can see this particular, how the basic block gets transformed into SSA form. So when we are looking at a use, we have to see what is the particular definition that is reaching that use. Similarly, in this basic block, the definition that is reaching this particular use of x is the definition x2. So we replace this use x with the x2. And here we are defining, there's a new definition for variable y. We have used the version y1 already. So we have to use a new version of the variable y2. So y2 is equal to x2 minus 3. Great. Now let's come to this basic block. In this basic block, if you see this variable x, so what are all the definitions that are reaching this use of variable x? So along this path, the definition x2 is reaching, and along this path also the same definition x2 is reaching. So either when we execute the program, either the program takes the if part or the else part, the definition that is reaching this particular use is the same definition x2. So we are perfectly good. So we say x, we replace this use of x with x2. But then there is a problem with variable y. Okay, let me clean up this slide so that now it becomes clear. Now, but there is a problem with variable y. What is the problem with variable y? If you look at variable y, so if you look at this particular use of variable y, if the control flow takes this particular path, then the definition that reaches this use is y1. So along this path, y1 is the definition that will be reaching this particular use, and along this path, y2 is the definition that reaches this particular use. When there are two definitions reaching a use, then we are in trouble because we don't know whether we should be using y1 or y2 here. So this is what usually when we are transforming code from to SSA form, these split points are not a problem, but join or merge points, they can cause problems. These are join or merge points. That is, a basic block has multiple predecessors, then it's a problem. But if there is a split, that is when a basic block has multiple successors, it's not a problem. But when it has a multiple incoming predecessors, then it's a problem, because multiple definitions can reach a particular use, and we have to resolve it. So how do we resolve it? The way we resolve it is by introducing what is called as a phi function. So phi function says, so phi function y, so and then, so phi takes two variables. So the definition y1 that is coming along this path, and the definition y2 that is coming along this path. So these two are the parameters. So y1 is coming along this path, and y2 is coming along this path. These two parameters are taken as input by the phi function. And when the program gets executed, depending upon whether the control, if the control comes like this, then what happens is the value of the phi function is y1. And if the control comes like this, then the value of the function phi is y2. And here we are creating a new definition y3, and this y3 is what reaches this use of y. So this is how multiple reaching definitions to a particular use is resolved by introducing what are called as phi functions. So we use a phi function to merge multiple definitions and create a new, or to merge multiple uses reaching a definition and create a new definition. So here we create a new definition y3, and this y3 is what reaches the use at this step. So going back here, so what are we doing here? So here we just use, so we say y3 is equal to phi of y1 comma y2, and this one we replace it with 3. So this definition is reaching this use. And what is phi function? What does phi function says? So if the control flow is coming along this path, then not along this path or just from this edge, then phi function returns y1, and if the control is coming along this path, then phi function returns y2. So let's look at this one more. We'll look at a couple of more examples before we conclude this class, so that we can start afresh in the next class. So here is a example code, and which computes the max of 3 numbers. And this is the, when it gets translated to a control flow graph, this is the control flow graph that gets generated. If you see what happens is there are multiple paths. There are, if you look at the sprint mags statement, then the mags that that is being used in this printf statement, there are multiple definitions that reach that use. So along this path, the definition max1 reaches the use, this particular use of max. And along this path, there is a different version of the variable max2 that comes. So if you see this code, so this is max1, this is max2, this is max3, this is max4. Remember, in SSA form, if you look at the code on the LHS of a statement, a variable can occur exactly once. So earlier the max variable is on LHS at 4 different points, but after changing it to SSA form, we have generated 4 different versions of the variables, max1, max2, max3, and max4, and that resulted in this control flow graph in its SSA form. But the problem is, if you look at this particular use of max, these are all definition points. This is definition point D1, this is definition point D2, this is definition point D3, this is definition point D4. So here this is D1, D2, D3, D4, and there is one particular use U here, let's call it as U1, there are 4 different definitions reaching the same use: D1, D2, D3, D4. So, and then there is one particular use U. So there are 4 different definitions that are reaching this use. So when there are 4 different definitions reaching a particular use, then it becomes hard for us to figure out which particular definition to use, because the particular definition to use depends upon the particular control flow which the program takes. So what do we do? So what we do is we jam all these definitions by introducing a phi function. Okay, so what do we do? So we jam all these definitions by introducing a phi function. We say max5 is equal to, so phi of max1, so on max4. So we jam all these definitions and we create a new definition max5, and then this max5 gets propagated to the use that is there before. And that's what exactly is happening. So we are jamming the definitions that are coming in multiple directions by introducing a phi function, and we are creating a new definition and a new variable max5, and this particular definition, it gets propagated to this use. Great. But then you could be wondering, so, but how will the program know? But there is no such instruction as phi function in the machine code. So how do we know when the control flow reaches this basic block, when the control flow reaches this basic block, how do we know which particular path we took to reach this basic block? So it's an important question, and that's what the answer is also simple. There's a simple way to resolve it. But what I would like you to appreciate is we take the original code and transform it into SSA form, and we do all sorts of optimizations on the SSA form. And after all these optimizations are done, finally we want to resolve or take care of these phi functions. So we will see how we will this phi function is taken care of at one level. So what we do is we introduce in these predecessor basic blocks, like for example here we say t is equal to max1, t is equal to max2, t is equal to max3, t is equal to max4. These statements we introduce in the predecessor basic blocks. And then we say max5 is equal to t. So if the control flow comes along this path, then the value that gets assigned to max5 is max1. And if the control flow comes along this path, then the value that gets assigned to max5 is max2, so on and so forth. So this is how we can translate or take care of the phi functions in the SSA form. You take the original code, convert it into SSA form, do all the optimizations, and after you're done with all the optimizations, you what do? So you eliminate the phi functions, because there is no physical realization of phi functions at the actual processor level. We have to take care of it in a different fashion. And one approach to take care of it is by this particular transformation that you are seeing here. Let's look at one more code to see how code can be translated into out of SSA form. In this particular example, along this path, if the control flow comes along this path, phi should return x0, and if the control flow comes along this path, this phi should return x1. And how do we translate it into out of SSA form? So in this basic block, we just say x2 is equal to x0, and in this basic block, we will say x2 is equal to x1, and here we just use y is equal to x2. So if the control comes along this path, y contains x0, and if the control comes along this path, then y contains x1. Again, I repeat, you start with the original code, you transform it to SSA form, you do all the optimizations, and once all the optimizations are done, we want to get away with the phi functions, and the way to get away with the phi functions is like this. This is one approach. I will conclude this class with a small catch that you have to be careful while translating code to SSA form. Let's say you have your control flow graph is like this. This is your original control flow graph. Due to lack of space, I'm writing here x is equal to x plus 1. There is a loop, and then this is where you are returning, and you are returning x here. And when you transform it into into SSA form, this becomes x1, this x becomes x1, all right. And then along this path, a version of the variable x3 comes, and along this path, a version of the variable x1 comes. So what we do is we introduce a phi functions. There are multiple definitions that are reaching this particular use. There are multiple definitions reaching this particular use. One is x1 and another is x3. So we don't know whether to replace this x with x1 or x3. So what we do is we introduce a phi function to merge these reaching definitions. So we say x2 is equal to phi of x1 comma x3, and then we change the statement x is equal to x plus 1 to x3 is equal to x2 plus 1. I want you to remember this example, understand this example carefully, because this example shows how to translate control flow graphs into SSA forms when there are loops present. So this is a canonical example for it. You should pay attention to this. This is very important. So you do optimizations on this, and if you take the previous approach to translate the code into SSA form, so what you do is, if you want to take this code, this is the SSA form code, and you want to translate it into out of SSA form, you go to the predecessor basic block. So the first predecessor basic block to this is this. So you introduce a temporary variable. We say t is equal to x1. And then the other predecessor basic block for this basic block is itself. So at the end of this basic block, we will say t is equal to x3. So what happens is, if you are coming along this path, you have t is equal to x1. If you are coming along this, and if you are coming along this path right here, if you are coming along this path, you have t is equal to x3. So depending upon whether you are coming along this path or coming along this path, the value of x2 will be either x1 or x3. So this is how you can translate the SSA form representation here into out of SSA form representation here. But if you want to get away with not using a temporary variable, and if you think, why not we use x2 is equal to x1. So here you may be tempted to say, along this path, I will say x2 is equal to x1, and along this path, x2 is equal to, yeah, that's true. So along this path, x2 is equal to x3. Then there is a problem, because when you exit from this loop, the value of x2 that gets returned is the incremented value of x2. But we just want to return x2, but what we end up doing is we end up returning an incremented value of x2. So this is an incorrect translation. This is an incorrect translation, wrong translation. So yeah, I think I shot overtime today. But to conclude, the example that you are seeing here is very important example. It illustrates two ideas. Number one, it tells you how to translate control flow graphs which contain loops into SSA form. So there is a small canonical example here. You should work through this example and you should understand. The second point that you should understand is if you want to translate something out of SSA form, if you are not careful, you will end up making mistakes. So for example, here, what you are seeing on the rightmost is the correct translation, and what you are seeing in the middle, it is not a correct translation out from the SSA form. That's all I have for today. So please review these ideas once before you come to the next class.